The rational zero theorem says if f of x equals a sub n times x to the nth plus all of your other terms all the way down to the linear term a sub 1 times x plus the constant term a sub 0, as long as that polynomial has integer coefficients, then every rational zero of f has the following form: p divided by q, where p represents a factor of the constant term a sub 0, and we're going to divide that by q, which represents a factor of the leading coefficient. Which in this example is a sub n. So we take each factor of the constant and divide it by each factor of the leading coefficient. And that will give us all of the possible zeros of the function. So all of the possible x-intercepts. They won't all be a 0 or an x-intercept of the function. We'll have to do some other tests then to figure out which ones are and which ones are not. But it gives you all of the possibilities. So let's list the possible rational zeros of f using the rational zero theorem. So in our first example, f of x equals x cubed plus 2x squared minus 11x plus 12. So first of all, recognize that your constant term is 12. So p will be all of the factors of 12. We have to consider positives and negatives. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And the leading coefficient is 1, since there's nothing written there. So q is going to represent all of the possible factors of 1, which is just plus or minus 1. So then p divided by q, well, we'd have to take each of our factors of p and divide it by each of the factors of q. But luckily in this case q is just 1, and dividing by 1 won't change anything. Possibly just the signs, but we're already considering the positives and negatives. So that means that the possible zeros in this case were really just the factors of the constant, because the leading coefficient was 1, and dividing by 1 wouldn't change anything. So these are our possible zeros for the first example. Let's take a look at another example. So this time our constant is negative 10. So p, factors of 10, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Our leading coefficient is 4, so q, the factors of your leading coefficient are plus or minus 1, plus or minus 2, plus or minus 4. So p divided by q are possible rational zeros. Well, I'll start by taking my first factor of p, which is 1, dividing by my first factor q, which is 1. So 1 divided by 1, gives me plus or minus 1. And I'll take 2 divided by the 1, because I do this one divided by this one, and then I'll do 5 divided by 1, and then 10 divided by 1. Then I'll have to do them each divided by the 2. So I'll have 1/2. 2 divided by 2 is 1, which I already listed, so I don't have to list it again. 5/2. And 10 divided by 2 would be 5, but again, I already have that, so I'm really only adding on plus or minus 1/2 and plus or minus 5/2. And then I have to take them each and divide by the 4. So I'll have 1/4. 2/4 is 1/2, which I already have. 5/4 and 10/4, but 10/4 is 5/2, which I already have. So I'm just adding on 1/4 and 5/4. So those are all the possibilities for p's being divided by q's. Therefore, these are all of my possible zeros for that example. So once we figure out what all the possible zeros are, we're going to use the process of synthetic substitution to quickly determine which ones actually are zeros and find all of the actual zeros for the function. So we'll start by identifying the possible zeros. So my constant is 20, so p, factors of 20, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. My leading coefficient is 1. So for q, my factors of 1 are just plus or minus 1. Dividing by that wouldn't change anything but the signs, and I'm already considering all of the positives and negatives. So therefore, these are my possible zeros. Let's start to try and figure out which ones actually are a zero. There's really no good strategy to this, just looking at your possible zeros and the function. You can use intuition, a little bit of guess and check. We've just got to try things until you find one that works. Once we find one that works, we can factor it down and strategically solve with algebra. But in the beginning, we just got to get kind of lucky until we find one that works. So I'm going to start by testing positive 1. I'm going to list all my coefficients from the original function. So the x cubed coefficient is 1, the x squared coefficient is negative 8, the x coefficient is 11, and the constant is 20. So I make sure all my place values are there. I've got cube, squared, linear, constant. Remember that your first term comes straight down. Your leading coefficient, nothing happens to it. Then we start the process where we take this number and multiply it by the outside and put it under here. So 1 times 1 is 1. Then I add straight down in my column. So negative 8 plus 1 gives me negative 7. Then we're going to take the negative 7 times the 1 and put that in the next column. So negative 7 times 1 is negative 7. Add straight down, we get 4. Then we take the 4 times the 1 and put it in our next column. That's 4. 20 plus 4 gives me 24, which is not 0. So 1 is not a 0 of this function, and I have to move on and try another. I'm going to try negative 1. Again, leading coefficient comes straight down. Then I take that times the number I'm evaluating for and put it in the next column. I add straight down. I multiply these two and put it in the next column. I add straight down. I multiply, I put it in the next column, and it looks like I'm about to get lucky. I do in fact get 0, meaning that negative 1 is an actual 0 of the function, or an x-intercept. Okay, so now I'm going to pull out all of the useful information from these values. So what this is telling me is my first factor would be x plus 1. Because when I set this equal to 0 and solve, I'd subtract the 1 and get the negative 1 that I now know is a 0. And then I pull out my other coefficients, so this means x squared minus 9x plus 20. Because remember that this final value would be your remainder. There isn't any. And so this is my constant, my linear, my quadratic term, because it started as a cubic and I'm dividing out 1. So I'm down to a quadratic. And now I can factor that. And if I couldn't factor it, I could always do quadratic formula. But this is going to factor into x minus 4x minus 5. So I'm going to set this equal to 0 and use zero product property to solve for my 3 zeros of this function. So this is the one I got lucky and found originally. Once I've had that one, it allowed me to divide it down to be able to find these two. So I know that the 3 zeros of this function are negative 1, 4, and 5. Okay, on to our next example. So our constant is -35. So for p, the possible factors are plus or minus 1, plus or minus 5, plus or minus 7, and plus or minus 35. Again, the leading coefficient is 1. So the possibilities are 1 or -1. So that means that these are really my possible zeros, because dividing by plus or minus 1 would only change the sign, and we're considering all the positives and negatives already. Okay, so again, just start somewhere. If you have a good feeling about one, go for it. If not, I like to just start at the beginning to stay organized. But test things until you find a possible zero. List out your coefficients. Again, make sure you've got every place value. So here's cubic, quadratic, linear, constant. Nothing happens to the leading coefficient. It comes straight down. We're going to multiply these, put it under this column. We're going to add straight down. We're going to multiply these, put it in your next column. We're going to add straight down. We're going to multiply, put it underneath, and so I know right away I'm not going to do it. So I have to try something else. So I'll try -1. Leading coefficient comes straight down, multiply, add, multiply, add. Again, unfortunately, not a 0, so I'm moving on to 5. Leading coefficient comes straight down, and multiply, add. Woohoo! We found a 0. So we know that 5 is a 0, meaning that x minus 5 must be one of the factors. This is your constant. This would be your linear term. This would be your quadratic term. So that means my other factor is x squared plus 7. I cannot factor x squared plus 7, but it can be solved with square roots, so I'm ready for the zero product property. And again, I know this one. This was the one I found via synthetic to get me rolling on this problem. This one I can solve with square roots. Isolate the squared term. Take the square root of both sides. Remember that when you have a square root, you put a plus or minus down if you're solving an equation. When you have a negative under the square root, you've got to split it up into -1 times the other number. And so we're going to have two imaginary solutions for this one. We found 3 possible zeros: +5, positive I square root of 7, and negative I square root of 7. So this is the only real 0. So it's only actually going to cross the x-axis at 5. And then the other 2 zeros are imaginary. Okay, on to our next example. So your constant is 12. So p, the factors of the constant, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Q, well, our leading coefficient is 10, so factors of 10, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. So unfortunately this time I do have to go through the whole process of p divided by q to find my possible zeros, because my leading coefficient wasn't just 1. Okay, well first I'll take all my p-values and divide them by plus or minus 1. So I'll get all of these. Then I'm going to have to take them each and divide them by 2. So 1 divided by 2 will give me a half. 2 divided by 2 gives me 1, which I already have. 3 divided by 2 gives me 3 halves. 4 divided by 2 is 2, which I already have. 6 divided by 2 is 3, which I already have. And 12 divided by 2 gives me 6, which I already have. So now I'm going to move on and divide everything by 5. So I'm going to have plus or minus 1/5, 2/5, 3/5, 4/5, 6/5, 12/5, and then I have to take everything and divide by 10 for my final possibilities. So I'll have 1/10, 2 divided by 10 reduces to 1/5, which I already have. 3/10, 4/10 would reduce to 2/5, which we already have. 6 divided by 10 would reduce to 3/5, which we already have. And 12 divided by 10 would reduce to 6/5, which we already have. So there's my list of possible zeros. And looking at this list, it's pretty daunting. There's a whole lot of possibilities here, and it could take a very long time in order to get lucky and find one that works. So hopefully you're thinking by now there's got to be a better way. And that better way is through technology. We can graph this function and take a look at the graph, find its x-intercepts, and find a good starting point. If we can locate at least one zero on the graph, then we can start our process of synthetic division and really dividing it down to find the other possible zeros. So let's graph this. Okay, so if you graph this function in Desmos or your graphing calculator, it looks kind of crazy, but you can identify at least one x-intercept at -1/2. So that's where I'm going to start my synthetic division process. So my coefficients, my quartic, my cubic, my quadratic, my linear, my constant. Leading coefficient comes straight down, nothing happens to it. 10 times -1/2, well half of 10 is 5, and so this will be -5. Add those two together, get -16. Negative times a negative will give you a positive, and half of 16 is 8. Adding -42 and 8, we get -34. Again, a negative times a negative is a positive, and half of 34 is 17. So if we add these two together, we get 24. Half of 24 is 12, so this will be -12, and woohoo, there it is. There's the zero that we predicted. So, this is constant term, linear term, quadratic, cubic. So I really need to be able to find one more possibility in order to continue on. I need to factor it down at least a little further. So I'm going to just build my synthetic right off of what I have there. I don't need the last column anymore. But now I'm down to 10x cubed minus 16x squared minus 34x plus 24. So I can just keep going with my synthetic and build another row on. If I take a look at my graph, if I look at this point right here, it's between 0 and 1. So my possibilities there, it's beyond 1/2, but it's before 3/4. So I think a pretty good guess there would be positive 3/5. So I'm going to try that and see what happens. Leading coefficient comes straight down, nothing happens to it. If I take 10 times 3/5, Well, 3/5 means to multiply by 3 and divide by 5. So I'm going to divide first. 10 divided by 5 is 2, times the 3 gives me 6. Negative 16 plus 6 gives me negative 10. So negative 10 times 3/5 will just give me negative 6. And again, I get that by doing 10 divided by 5, which is negative 2. And then I take that negative 2 times the 3, to get negative 6. If I add straight down, I'll get negative 40. So again, I'm going to take negative 40 and divide it by 5. That'll give me negative 8 times the 3 gives me negative 24. Woohoo, that was right. There's our next. Okay, so let's write this out in factored form. We know that x plus 1/2 must be a factor in order to get negative 1/2 when we solve it. And x minus 3/5 must be a factor. And then we have x squared minus 10x minus 40. Oh, I'm sorry, 10x squared. Can't forget that leading coefficient. So 10x squared minus 10x minus 40. So we're trying to find all of our zeros. From that trinomial, I can factor out a 10. So I'll go ahead and do that and have 10 times x plus 1/2 times x minus 3/5 times x squared minus x minus 4 equals 0. Move everything up so a little more space. Okay, so that 10 we can actually think of as 5 times 2 and make this factorization look a little more like what we're used to. Because we're going to distribute those back into these first two. So we don't have fractions. We don't factor into fractions. We use integer values. And then this trinomial, I cannot multiply to negative 4 but add to negative 1. So I'm going to have to bring in quadratic formula. But again, this 2 gets absorbed here. The 5 gets absorbed here. So that 2 times x gives me 2x. 2 times 1/2 is 1. 5 times x is 5x. 5 times negative 3/5 is negative 3. So that just looks a little more standard, and it still gives you the same zeros. If you solve this, you'd subtract the 1 and divide by 2 for negative 1/2, and if you solve this, you'd add 3 and divide by 5 for the 3/5. For a quadratic formula here, a is 1, b is negative 1, c is negative 4. So x equals the opposite of b, which would be positive 1 plus or minus the square root of the b value squared minus 4 times a times c, all divided by 2a. So of 1 plus or minus the square root of 1 plus 16 over 2. So of 1 plus or minus the square root of 17 over 2. 17 is prime, so I can't break it down, so here's my exact solutions. So my zeros, this one I know gives me negative 1/2. This one gives me positive 3/5, and then we just solved with quadratic formula for the other two. So the real zeros of this function, you can see on the graph there's 4 of them, and we just found them to be x equals 1 minus the square root of 17 over 2, negative 1/2, 3/5, and 1 plus the square root of 17 divided by 2. Those are all of the solutions. So the process to finding all of your rational zeros. We use the rational root theorem. We take all of the factors of the constant, divide it by all the factors of the leading coefficient, making sure to always consider positives and negatives. Then we can graph the function, find its x-intercepts to find a good starting point to help the process become more efficient. And then we just start using this process of synthetic division to divide it down until we get all the way down to a quadratic that we can solve with either factoring, square roots, or the quadratic formula.